Hey everyone, this is Morgan. We're on page 4 of the Acids and Bases outline for Honors Chemistry. And we got a couple of terms that we're going to talk about here before we start getting into some math. And our first one is polyprotic acid. So if you use your language skills, I think you'll recognize that the prefix poly refers to multiple, and protic actually refers to protons, or in this case, hydrogen ions, which are just protons. So a polyprotic acid is capable of ionizing more than one H+ ion. Okay? The most common that we're familiar with is sulfuric acid, H2SO4, which can react with water to produce H3O+ and HSO4-. You see, the hydrogens do not come off all at once. It's a stepwise process. So in this first reaction, it is ionized the first hydrogen, leaving the hydrogen sulfate ion. Then the hydrogen sulfate ion, HSO4-, can react with water, and that's going to give us H3O+ and SO4-2-. So what we're seeing here is a stepwise ionization. And in this, we get a really interesting species, HSO4-. I've already shown right here how it can lose a hydrogen. However, because it's negative, it could also gain a hydrogen. So we say that it is amphoteric. That's the current term. We used to use the term amphiprotic, which I liked a little bit better because it had protic in it. And that means it is a species that is capable of acting as either an acid or a base. It all depends upon the situation that it's in. If you have a situation that tends towards production of hydrogen ions, it would act as an acid. And if you have an excess of hydrogen ions, it would act as a base. Water is a wonderful example of an amphoteric species. Okay. The other term that I want to get into is indicator. An indicator is a substance capable of existing in one of at least two different structures, depending on pH. And when it does this, changes its structure, it changes color. So it can actually tell us a lot about the pH of a solution. So I'm linking down in the comments what I call the red cabbage demo. Pause this video for a minute, go watch the red cabbage demo, take some notes, and then come on back. Okay, I hope you enjoyed that. So now what we're going to do is we're going to start into many pages that are a mathematical treatment of acids and bases. And we need to remember that the reaction that governs all of this is water auto-ionizing. 2H2O liquid turns into H3O+ aqueous and OH- aqueous, and I can write an equilibrium constant that we will call Kw for this, and it equals H3O+ times OH-. We don't divide by water because it's a pure liquid. And this equals 1.00 times 10 to the negative 14th at 25 degrees Celsius. It's an equilibrium constant. Okay? So, auto-ionization. This happens on its own. But as you can tell from the incredibly tiny value of this, it doesn't happen to any great extent. We get very little H3O plus or OH minus in a beaker full of water. Now, let me draw a really big rectangle here, and then I'm going to cut it diagonally. And this is going to be a graph of pH. And we're going to put pH 7 in the middle, and then this is lower than 7, so it's acidic, and this is greater than 7, so it is basic. And what we know is when we have a pH of 7, the concentration of H plus and the concentration of OH minus are equal. They're the same. And if you're looking here, it's because these form in a 1-to-1 ratio in a neutral solution. However, as you become more acidic, the amount of H plus increases while the amount of OH minus decreases. And if it's a basic solution, the amount of H plus gets much, much smaller, and the amount of hydroxide ion gets much, much larger. That's actually a really useful thing to remember. That's a good image there to tell you what's going on when something's acidic or basic. And sometimes folks will use the term alkaline when they're referring to something that is basic. All right, that's page 4. We'll continue this idea on page 5.